everyone, and welcome to Activity 13. Today we are going to talk about transformations of our rational functions. Now, our rational functions are a function that can be written as the quotient of two polynomial functions. And our most basic function is the reciprocal function that is a rational function. This is kind of like the most basic parent function. We also see 1 over x squared as another parent function. And we see here with 1 over x that we have this function passing through 1, 1, and 1, negative 1, with this kind of decreasing in the quadrant 1 or quadrant 3 value. And then 1 over x squared, it almost looks like a reflection. Quadrants 1 and 2 have those values, so that's the 1 over x squared parent function. Now, as far as the transformations of our functions go, parameter A deals with our vertical stretches or compressions. We also know if we have a negative out front of that, it would be a reflection over the x-axis. So that would look like a negative A value, and that outside the fraction or up top. Our parameter B is then the horizontal, not vertical, horizontal stretch or compression. And we see this as then the reflection over the y-axis if that's negated. And then with our shifts right and left, reminder when we think about even just going back to this function here, if we have x minus this c value, that would mean to the right, versus f of x plus c, that's to the left. And then last but not least, our vertical shifts, minus is down and plus is up. These ones are going to be a little bit more literal, so the plus d moves our graph up, minus parameter d would move our graph down. So on the next page, if we take the parent function 1 over x, we want to transform it for our first two graphs. So we see for this one, part 1 here is actually going to move it to the left 2 units because x is down there. And then we will also be moving our graph up 3 units. Now what we see with this parent function of 1 over x is that it has a vertical asymptote through x equals 0. It has a horizontal asymptote through y equals 0. So when we are transforming it, a lot of what's happening is we are taking our horizontal asymptote and it's getting shifted that up 3. That vertical asymptote is getting shifted to the left 2, so that we then would have this first and third quadrant kind of shifted up and to the left. In our next example, we notice we have a reflection out front there. So instead of our graph being in quadrants 1 and 3, what's going to happen instead is that these are going to reflect over the x-axis, and it's now going to reflect and look like it's in quadrants 2 and 4. So that's what the reflection will do. We also have on this one the shift of our graph up 2 units. So again, that will end up shifting that horizontal asymptote. Vertical asymptote would stay through x equals 0. And then again, we talked about reflecting those graphs so that it is now following along in those opposite areas. Now, just like we reflect 1 over x, we can also reflect 1 over x squared. This time, again, we are going to see a reflection. So instead of our parent function graph going up in this direction, it will reflect over and look like it is going down, reflect over that x-axis. We also see another shift, this time to the left 4, and we also have the vertical shift down 5. So moving this vertical asymptote to the left 4, the horizontal asymptote being moved, not up 5, down 5 units, because we have the minus 5. And then last but not least, again, these are being reflected downwards as opposed to upwards. So these graph, since it's x squared, would shift down from what this parent function was originally, both going up. Now this last one is asking us to move the graph here to the right 3 units and down 6 units. So we have right 3, so x equals 0 now moves to x equals 3. And then our horizontal asymptote is moving down 6 units. No reflections or anything else, so these are still going to be going upwards. We'd have that sketch shifted right and down. Now sometimes they are going to give us the transformed graph and we are in charge of making the transformations. So we notice on this particular graph, we reflected our graph so that it is now going down. So that's a reflection over the x-axis. And then we also have this graph being shifted up so that the horizontal asymptote is now through 4 instead of y equals 0. So we would take our original function 1 over x squared, and a reminder to reflect over the x-axis. We would negate that piece out front, and then the up 4 would be represented with the plus 4. So again, we see that reflection as well as that shift up. The next part of this then is asking us to shift first this graph to the right 3 units, and then we also are going up 2 units. Now this is the parent function without any reflections otherwise than that. So we would say on this one that we have f of x, since we're moving to the right 3, it actually is going to look like a minus 3, and then the up 2 would be represented on the outside with a plus 2. Finally, when we talk about domain restrictions for these graphs, again, algebraically, it's where our denominator is equaling 0, because again, we do not want the denominator to equal 0, otherwise we would get an undefined. So we would say it's all real numbers except for those that would cause the denominator to equal 0. So in this case, if we set our denominator equal to 0, subtract over the 2, we would say that our x is going to be all real numbers such that, that's what that bar means, except x cannot equal negative 2. Another way officially of expressing this would say, okay, all numbers from negative infinity until negative 2 or from 2 to infinity will in fact work out. On the next example, if we set x squared minus 1 equal to 0, we end up taking the square root of 1. So x is going to not be able to equal positive or negative 1 without some issues. So again, you might see that represented this way where we say it can be all x values except it cannot equal negative 1 or 1. Or we would say from negative infinity until negative 1 we're cool. Between negative 1 and 1 we're cool. Or from 1 to infinity. This would work out as our domains. Last but not least, if we set this denominator piece equal to 0, we see on here what multiplies to be negative 8 adds to be negative 2. Well, that's going to be negative 4 and positive 2. So x minus 4 and x plus 2. Each are going to have to get set equal to 0. And what we notice this time is that one of our zeros would be at, our undefined pieces would be at 4, the other at negative 2. So again, we could either say it, x can be anything except 4 and negative 2. Or, again, if we like interval notation a little better, from negative infinity until we get to negative 2, things are fine. Or from negative 2 to 4. Or from 2 to infinity. 4 to infinity. And not including those break pieces of our domains. Thanks everyone for watching. We'll work more with the next lesson in class.